Machine learning will bring out not just a new era of civilization, but a new stage in the evolution of life on Earth. Hello, I am Anjamini, final year computer science student at Tokaj Institute of Science and Technology. Today, let's discuss about leveraging edge computing through collaborative machine learning. This is the complete overview for today's presentation. This aims to propose a learning methodology that improves the prediction accuracy by leveraging edge computing through collaborative machine learning. Introduction. What is edge computing? It is what exactly it sounds like. Computing takes place at the edge of corporate networks, with the edge being defined as the place where end devices access the rest of the network. That's why we say it as a distributed architecture that features decentralized processing power. What is machine learning? It is an application of artificial intelligence. It provides systems to learn and improve from experience without explicitly programmed. Why do we need both? We know IoT environment comprises billions of interconnected sensing and computing devices. Things which sense and share contextual information, hereinafter referred to as context. Contexts are also capable of performing localized analytics like linear regression, outlier detection, and classification. The smart grid has been recognized as an important form of IoT since it allows a two-way contextual information flow, which produces new perspectives in energy management. Contextual parameters is relayed to a sync node, which is the backend system. So, we can process large amount of contextual data with comparatively less computing power and less network overhead. Literature review. The first method we are going to discuss is the efficient, scalable, accurate regression queries in DBMS analytics. It actually aims to incorporate advanced data analytics capabilities within DBMS. It contributes efficient analytic model and associated regression query processing algorithm. Moving to the pros of this method, it has an efficient algorithm, it is scalable and accurate, and many orders of magnitude is possible, and it is straightforward to implement. Over the pros, it needs high energy consumption and it needs high network bandwidth. Moving to the second method, it is querying framework in sensor networks. It is an average efficient querying framework to detect node similarities. SAF uses simple time series forecasting models. It builds these local models at each node, transmit them to the root of the network. Now, let's discuss the pros of this method. It also has an efficient algorithm. It is provably optimal in number of clusters. It can capture similarity between far away nodes that are not geographically adjacent. Over the pros, it takes over a week to give correct output, and it consumes high energy and it needs high network bandwidth. The above two approaches were very straightforward to implement but has gross disadvantages such as high energy consumption and high network bandwidth due to the streaming of raw data over the edge network. The third method is the most familiar topic nowadays. It is AI virtual assistant. It is an application program that understands natural language voice commands and completes tasks for the user. It sends and prepares data requests to a concentrated server. Advantages of these methods are it improve recommender system and it improve our workflow. And the disadvantages are security could be an issue sometimes, and it need high latency and it need high bandwidth. Now let's discuss about leveraging edge computing through collaborative machine learning. Energy consumption or IoT environment with sensors and sinks are used in this formation. The path is led from sensors to sink and sensors are only connected with one sink. Each sensor SI gather data contextual about the space around it. Each contextual data at time t consists of the multivariate vector x element of r raised to d, which referred as input, and scalar y element of r, which is referred to as output. Vector x and scalar y can represent any data sensed by the sensor. For example, temperature, humidity, acidity, carbon dioxide concentration in atmosphere, where we seek to learn the local regression function fi such that x to y at node si. One of the main challenges faced here is the collection of context from the sensors. By assuming that there exists a linear relationship, this linear model allows us to predict y based on the input x. The given formula represents the hypothesis S theta of x of the d-dimensional linear model. That is, h theta of x equal to theta 0 plus sigma k equal to 1 to d theta k xk, where theta k represents the weight of the local linear regression function that is determine the mapping between xi and y. This figure shows the easy IoT environment we discussed earlier. This is sink and these connected nodes are sensors. Sinks are interconnected to each other. One sink with its sensors are called query. Now let's discuss about edge-centric learning. Resources in a sensor are reserved for communication, processing, and data sensing. It has already been established that data transmission consumes much more energy when compared to the processing and data sensing task. In the proposed approach, the sink does not collect any data from the sensors. Instead, it stores all function fi. It is worth noting that each function fi models only the relationship between x and y from those vectors x captured by sensor si. Under edge-centric learning, it comes local regression model. In a network of n sensors and each sensor Si is receiving a context pair x, y at time instance t, since each sensor has limited resources. After a period of learning, the model's parameter theta I is derived from Si to the sink. The next method is local quantization model learning. Here, they further enhance learning model by extracting clusters for each sensors. Using these clusters, the system is able to determine whether a function fi is familiar to the input x or not given a query q of x. To estimate clusters for each Si, they used the online k-means vector quantization algorithm. After receiving the trained linear models and the corresponding K clusters from each sensor SI, the sync node has all the information available to proceed with query analytic task. That is, to answer the regression query Q of X. To predict the output y-cap more accurately, they proposed two algorithms which define closeness. First one is distance average. Distance average define closeness R of function fi to the query of Q of x as the Euclidean distance between the query point x of the regression query Q of x and the closest cluster Ci star from the cluster set of f. Ri equal to modulus of x minus Ci star. This is how it is represented. The given algorithm is for edge-centric learning function. First, inside the sync function, as we said earlier, the model's parameter theta I is delivered from Si to the sync. So, the local model, that is the corresponding thetas, are sent to the sync at a fixed number of steps t, hereinafter referred to as local epoch. It defines the number of training context pairs used to locally train the regression model before transmitting it to the sync. Then, in step 8, it comes the sensor function. They assign the time instance small t to 0. Then, inside a while loop where time instance small t is less than the fixed number of steps capital T, we assign the new pair x, y as context of time instance small t. For every new pair of x, y captured at sensor Si, updates both on time regression parameter theta I and the cluster vectors C. For each cluster C, we record the number of times it been updated L of C and prediction error E equal to y minus y cap the whole square, where y cap is the prediction equal to Fy of theta comma x. In the 16th step, the value of neta can be either 0 or 1. Then we return the cluster vector's value and pass it to the sync. The second algorithm which defines the closeness is reliable average. As we saw in the above algorithm, a low distance x minus c and a low error E are rewarded while a low number LC value is penalized. Given a regression query Q of x is issued to the sync, the closeness Ri is computed for each linear model Fi. The subset of models capital F, subset of set F1 up to Fn which are involved in the prediction y cap of the regression query Q of x are the models with the top C closeness values, with C equal to mod F, which is the models, and which is less than or equal to n. Then the prediction y cap derives from the average of predictions y cap j equal to fj of x such that fj element of f given the query Q of x. That is, it can be represented as an equation in the form y cap equal to 1 by c into summation of j equal to 1 to c fj of x such that fj element of f. Now, let's move on to the performance evaluation. Evaluating this method with sensor networks which have power and computation limitations, thus adopting machine learning models to greatly improve prediction accuracy and increase efficiency. For the analyzation, they used the real air quality data set collected from air quality monitoring stations in Beijing to evaluate the prediction accuracy of this method. We all know as many of data set we provide, we could attain that much accuracy in the result. There were n equal to 36 independent sensors, that is IoT devices transmitting knowledge to the scene. So there were n equal to 36 different local regression models. For example, let's consider Y as the contextual parameter which represents the concentration levels of nitrogen dioxide. These gases were emitted by combustion process and has a negative impact on human life. That is, we know nitrogen dioxide is linked with the summer smoke which is more dangerous to human. This figure shows the whole normalized dataset with a global linear regression plane over context pairs x, y. The prediction accuracy of this methodology with baseline and average solutions are assessed. Sensitivity of model was analyzed with respect to C, number of models to average, K, the number of clusters per device, and T equal to 100, which is the number of epoch. Now, let's move on to the advantages of this approach. It gives an increased prediction accuracy, it increases the efficiency, it has lower latency because the data packets need not to be traveled further distance. Since the data sets are improved and the machine is well trained, we get an output more faster. It has an increased bandwidth. Even though it had lots of advantages, this method faced some challenges such as to train the machine, large number of data sets were required. It presumes a large stable environment while in real world it can be constantly changing. Since this is a test scenario for sensor SI, each test data was taken. This method results for a better future. Let's see what are they. By increased bandwidth of local network, it improves the other services such as local servers, etc., which benefits in machine learning. Applicability of RA model, that is the reliable average model variant in deep learning task, is non-identical distributed. So, the proposed methodology can be further enhanced. This should serve as a reference point for further research in the field of collaborative machine learning environment. After comparing the several edge computing and machine learning techniques, our conclusion is such that our method focuses on leveraging the network edge with machine learning distributed over IoT sensing and computing devices for improving prediction accuracy and communication efficiency. Through two variant models, that is the distance average and reliable average, successfully increases prediction accuracy. By aggregating pieces of knowledge from similar local regression models derived from sensors, Adopting adaptive vector quantization. Now, let's see the references we used for this presentation. These are the several references we used in this presentation. Thank you all for your patience to hear me. Have a nice day.